So what we have here on the screen are some points about endothermic and exothermic reactions. We're just going to speak about them very briefly. It's not going to be the main focus of our reaction types. That's why I put them at the end here. Under endothermic reactions and exothermic reactions, you'll see that I basically put the same 4 points, but changed the words slightly. So for example, the first point indicates whether or not energy is used or energy is given off by the reaction, because that's the thing that's different between endo and exothermic reactions. What that means is that for endothermic, the products have more energy than the reactants, and in exothermic, they have less. So you'll notice I'm highlighting the word that's different in each of the statements. For the third point, we're talking about temperature. It decreases for endothermic and increases for exothermic. And I'd like to just make a little point about this whole temperature thing. Sometimes people find it confusing to hear that I needed energy for this reaction to occur, so I absorbed energy, and somehow that made things get colder. When we're talking about the temperature of the reaction or that it feels cold, what we're really measuring in these things here is the environment of the reaction. It's hard to see a chemical reaction. You can see the evidence that it happened or that it's happening, but it's really hard to see the molecules themselves. And so often, chemical reactions happen in another substance. For example, a lot of chemical reactions happen in solution. I dissolve things in water, that makes them react with each other. And so what I'm really measuring is the environment of the reaction, what's happening there. Because the reaction itself is sucking energy from the environment into its bonds that it's creating, and that's why we're saying energy is being used up. The same is true for exothermic. The reaction is actually putting energy into the environment, and so what we can detect, let's say the air around a fire feels hot because the fire is giving energy to the air around it. That's just a little point that I wanted to mention, not necessarily because I'm going to ask you that detail specifically, but for future chemistry courses where the discussion of endo and exothermic becomes greater, that would be a really important thing to understand. What I do want to point out here, look at what the words are spelt like. Endothermic, maybe think about the word enter. Exothermic, maybe think about the word exit. Energy is entering or is exiting, and that's how you can use a little trick to remember what endo and exothermic mean. Now in terms of us, what we're talking about, it's this first point that would be like the definition of it. In an endothermic reaction, energy is used. And so I'd just like to show you that the categories we already discussed are not mutually exclusive from these two. This is a different way of categorizing reactions. For example, a lot of decomposition and single or double replacement reactions are all actually endothermic reactions. For exothermic reactions, definitely combustion, a lot of formation reactions, as well as single replacement and double replacement, can all be exothermic. And so the categories we already saw could fall into these two categories as well. So what I realistically might ask you is, when I describe a reaction, could you tell me both categories? Could you tell me, for example, that it's a formation reaction and that it's exothermic? That would be something that I would ask about. And the way you'll know is whether energy is given off or energy is used up. That will be the key characteristic difference. Now, I know I heard someone say, I sucked at this in grade 9. Luckily for you guys, this is a minimal point for what we're discussing right now. You'll just have to recognize whether energy was used or produced or given off. And there realistically would not be a lot of questions about this on your unit test, since it just took me about 6 minutes to discuss it, and this is the only day that we're discussing it on. Does anyone want to ask anything about endo and exothermic reactions? All right, so we are going to move on to our last topic. What I'd like you to do is just think about the part that's at the top first. So if you want to write down those few points, and then I'll discuss them. So here's what it says in terms of moles, which is what we're talking about. A mole in chemistry is not a creepy animal that you find in the skimmer basket in your pool. It's gross. I had that happen once. Has anyone else ever found something creepy in the skimmer basket in a pool? You should check. If you know someone who has a pool, ask them, because really gross things sometimes turn up. But a mole in chemistry is a quantity of items. And so I want to say something about this word, quantity. In chemistry, from now until the end of you studying chemistry, whenever that is, whenever you hear the word quantity, you should think moles. A lot of the time people hear quantity and they think, oh, I'm supposed to measure the mass or the volume. But quantity always refers to how many moles of something we have. And so that word and moles go together. So a mole is a quantity of items, kind of like a pair represents 2, or a dozen represents 12, or something called a gross, which is awesome, represents 144, or a ream, like a ream of paper, a package of paper is usually 500. There are words that represent numbers. A mole represents 6.02 times 10 to the power of 23. So if I wrote that out, it would just be like that. Now, what that means is 6.02 times a 1 with 23 zeros. That's what we're talking about there. When we get to using that number, I'll make sure that you know how to type this into your calculator, because it's slightly different depending on the type that you have. But that's how much 1 mole is. So it's an incredibly large number. We use this really to measure atoms and molecules. The logic is an atom is so small that it's really hard for me to measure anything about just one atom. So we needed a number big enough to give us measurable numbers. So you'll notice that on your periodic table when we look at it, we're talking about moles, not about individual atoms of things. And all of the masses that are on the periodic table are reasonable numbers. They're somewhere between 1 and, say, a couple hundred. They're not really, really tiny decimal numbers or really, really huge numbers with large exponents. And so that would be the logical reason that we talk about moles instead of individual atoms. So that's what a mole represents. The second part is about molar mass. And so we're interested in this second section of the page here. I'll just read out the points in case they're kind of small. The first point says that molar mass is the mass of 1 mole of an element or a compound. For example, carbon is 12.01 grams per mole. The second point says the molar mass for every element is on the periodic table. And the third point tells you how to get the molar mass of a compound. So I'll just pause. So the first 2 points are really just informational. Molar mass is the mass of 1 mole. That means it's the mass of 6.02 times 10 to the power of 23 atoms. I'd like to really specifically point out the unit, grams per mole, which I could abbreviate with a G and then a slash and then MOL. That is the unit. Now, when we get to the second part of this discussion, which is doing some calculations, what I'd like to show you is that you could use a formula, but you won't always have the formula available to you on a formula sheet. In grade 10, sure you will, but in the long run you won't. And knowing the units of something like this is very helpful when you're trying to calculate things. And so that's the unit. If you ever forget, that unit is on the periodic table. So on your periodic table, on the right side, there's a little box. It's iron as an example, and it shows you what all of the numbers represent. And it even tells you that the atomic molar mass is measured in grams per mole, in case you forget. So every element's mass is on the periodic table. For example, in the example we're going to do down here, sodium is the first one. If I look in sodium's box on the periodic table, there's Na in the middle, there's an 11 on the top left corner, and 22.99 on the top right corner. It's this number, top right corner, that we're looking at. Now, if I ask you what's the molar mass of an element, that's pretty easy. It's right there on the periodic table. But the molar mass of a compound is a little different. It's not on the periodic table. We have to do some work to figure out the molar mass of a compound. To do that, we have to add up the sums of the molar masses of all of the atoms in that compound. And I'd like to highlight the word all. That means that I have to account for every single one of them. It could be that there are several atoms of the same element. Like in this one, there's several atoms of oxygen. I have to count each one of them. So in my example, NaHCO3, which is sodium hydrogen carbonate, or more commonly sodium bicarbonate, or more commonly baking soda. I was watching the Magic School Bus this morning, because that's what you do when you have a 2-year-old, and in the episode, they were using baking soda and vinegar to help them get their Magic School Bus out of a cake that they were inside. It was quite funny. Can you go? Anyways, this is baking soda. We're going to calculate its atomic molar mass. We'll start out with sodium. Like we just looked, sodium's mass is 22.99 grams per mole. I have 1 atom of sodium, so in 1 mole of baking soda, sodium contributes that much to the mass. And then I'm going to add. My next element is the H for hydrogen. Hydrogen's molar mass is 1.01 grams per mole. I'll keep on going. My next element is carbon. Carbon's molar mass is 12.01 grams per mole. And then I'll end up with oxygen. So I'm literally just adding up numbers that I find on the periodic table. 22.99 plus 1.01 plus 12.01. And here, I need to do something. There are 3 copies of oxygen. I know that because there's a subscript. I have to count each of those atoms of oxygen individually when I'm talking about the mass. So for my last step, I won't just write 16, which is the molar mass of oxygen. I will write 3 times 16.0 grams per mole. Now, most calculators know the order of operations, but in case yours doesn't, it's possible that you might need to put brackets there. so that when you're doing this calculation, you know you have to multiply 16 by 3 first, and then continue on adding things up. So this is the first time when I think it would really be to your benefit to have your calculator out and about. If for whatever reason you do not have a calculator or you haven't bought one yet, you need to have a scientific calculator. It doesn't have to be a TI 83 or 84, but that's what typically you use for math. It has to be able to do exponents and powers. So as long as it says scientific calculator, that's good enough. You can get them for like $10. They don't have to cost $100. But try this in your calculator if it's here, and make sure that when you add 22.99, 1.01, 12.01, and 16 times 3, you end up with 84.01 grams per mole. And if you're typing that into your calculator and that's not what you're getting, then you probably have to put brackets around the 3 times 16. On my calculator, my TI-84, it knows that multiplication comes first. I don't have to put brackets, but it really varies depending on which kind of calculator you have. Does anyone have any questions that they'd like to ask here? Now I realize there's some stuff on the bottom of the screen, but I don't think we're going to get to it today. So what I'd like to do is just a few examples of figuring out the molar mass of a compound, because that's something that you would regularly have to do. So on the screen here, I would like for you to find the molar mass of the compounds or substances that you see here. Now to find molar mass, the first thing you need is the correct chemical formula. Then you will add atomic molar masses. So this is actually going to get you to review two things at the same time. One, correctly writing formulas, and two, adding up molar masses that you find on the periodic table. So just so everyone can see, I wrote the answers for molar mass questions up here so that you can check. And I made a little list of questions you need to do and questions that would be optional on the handout you already have to help you finish reviewing reactions.